Okay, so we are recording, and what's going to happen now is we're going to talk about circuit design and logic gates. So as I think you already figured out, there are going to be 6 logic gates that we're going to deal with. And I want to explain a couple of them, well, the first 2 anyway, in a form that you can understand. So first logic gate that we deal with is always an AND gate. An AND gate is where to have your circuit actually working, input 1 and input 2 need to be on. And the way we express that is through the logic, through using some logic. So this thing is a truth table. If we have our logic set here, these are the inputs, 1 or 0. Now an AND gate, just before I do that, let's go back to the days when we did science in stage 5. And you had your little circuit. So that's supposed to be a light, and we have a couple of switches. All right. For the light to switch on, both switches need to be on, correct? So switch 1 and switch 2. This is our logic. So therefore, for a 1 output, so the 0 output is light off, 1 output is light on. What has to happen? Both gates need to be on. So therefore, in terms of our logic, 1 and 1 gives 1. If one of these switches is open, the light doesn't turn on, correct? Okay, so 1 and 0 gives 0. 1 and 0 gives 0. And if both switches are open, what happens? Nothing. Okay? That's the logic of it. So you see how that works? Now, when we're actually drawing the circuit is a particular shape. And so we have our lines of input. We have this thing called an AND gate, which looks like a funky D. We have our output. So here's our input. There's our output. What's wrong? My terrible handwriting?
No, as soon as you drew that AND gate, I think every dude in the room looked at each other.
And you immediately said, it's a funky D
Yeah.
as well. And everyone's just going,
the same joke as I was.
Okay, I'm going to pretend I have no idea what you're talking about. Thank you, Margin. All right, so there's my inputs and outputs. And so therefore, when we're drawing the circuit, here's a truth table for it. 1s or 0s can be the only inputs, 1s or 0s can be the only outputs. So around the outside of the circuit, the table, we have inputs. Inside the table, we have outputs. Okay, it's really, really, really simple. There's our AND gate. That is the first gate that you learn. So when you're drawing a diagram, you see that shape, that is an AND gate. And there'll be other shapes for OR, NOT, XOR, etc. Okay? So there's my first logic gate. Second one we have to deal with is an OR gate. Once again, I've got the logic there. Once again, let's just think about this in terms of something that we already know. So let's draw our diagram from science. Once again, we've got our light globe. Okay, so for this light to turn on, what needs to happen? Either one of those gates needs to be on. So if I can complete the circuit, the light comes on. Correct. So when I do my logic gate there, 1, 0, 1, 0, once again, inputs go around the outside, outputs go on the inside. If both of the gates are closed, both of those latches are closed, what happens? Does the light turn on or not?
Turns on.
It does turn on. If one of them is on?
yes.
If one of them is on. If both of them are open, what happens?
No.
So there's my OR gate. Okay?
Yeah, L gate.
Sorry?
Logic gate, okay.
All right. So now when I'm drawing this as a diagram, we have, instead of it being a straight edge on this side like that would be, again, that's my AND gate. The difference will be that I have a curved edge in here. So there's my inputs. and there's my output. And that's my OR gate.
I can't not see it now. I wasn't seeing it like that before, but I can't not see it now.
Already got it.
I so don't think I'm putting this video up to YouTube. What the hell, I'm going to anyway. And you guys can look back at it and think, how filthy were your minds? All right, so that's an OR gate. Once again, when you have...
I'm not really focused. I've already seen. I've done this before. So.
You have done this before?
I
Oh,
sat in
good.
this classroom last year while you were doing this.
This is cool. All right, so there's my OR gate. Now, there are 4 other gates we've got to worry about. And unfortunately, I can't draw this diagram for any of them because I don't know what it's going to look like. But you get the point, okay? It's trying to have switches turn on and off.
How the hell does a not gate work again? I remember that.
All right, so, hey, Todd wants to know about a NOT gate. Let's look at a NOT gate. A NOT gate is simple. It's got one input, therefore one output.
Is it like a boolean?
It inverts the field. So if my input is 1, my output is not 1. What's not 1? My input is 0. What's not 0? That's it. So when you're drawing this one, you have your input, it's a triangle with a little circle, and your output. Okay? So this is literally an inverter. It turns a 0 into a 1. Simple as that. Notice that it looks different to other gates. Notice that it looks different in the sense that I have single input, single output. It doesn't have dual inputs. It doesn't have dual outputs. It's a single gate.
How do you actually draw this one as a circuit, or is that too weird?
We'll come to that. Let's just go through the other 3, and then we're going to start looking at circuits as well.
I cannot think of how that works.
No, that's okay. So your NOT gate, very basic, it's an inverter. And you can, if you wanted to, have your AND gate like so, and then chuck a NOT gate on it. And so therefore, if I have 2 1s as my input, 1 is that level of output, which is 1 at that level of input, which is 0 at that level of output. So yes, it's an inverter.
Can you just take the little circle from the end?
That's when I get to a NAND gate, yes.
Yeah, cool.
Okay. So there's an example of stringing 2 circuits together to make something else. Hello, sir.
Where would this be used? What's an idle?
This is what how a CPU actually does its calculations. I'm going to show you circuits, then I'm going to show you this is basic circuit design, and then I'm going to show you some specialty circuits, a half adder, a full adder, and a flip-flop.
Do we ever go down to the level of looking at transistors on the way?
A flip-flop is your basic unit for RAM. A half adder is your basic unit for a CPU.
Flip-flops are shooters.
Yes. So we'll look at a couple of specific flip-flops. A D-latch is the most common one.
What would be the need to?
It's funny how I know about
A need for an inversion.
redstone.
Because this is how our logic gates work, and you will see. All right, I'm going to draw a couple of specialised circuits that are used in CPUs. Todd, I'm going to draw a couple of specialised circuits that involve these gates and derivations of these gates. And in fact, you never draw a NOT gate. It's always attached to something else. Speaking of which, let's have a look at a NAND gate. So a NAND gate is
Not and.
is short for not and.
I'm a genius.
You're a genius. So you have your logic that you know for your AND gate, and you invert it. So you know an AND gate is 1 and 1 is 1. So what is a not and? 1 NAND 1. 0. Okay? It's an inverted AND gate. So when you're drawing it as a circuit with 2 elements, you draw exactly what I drew before. But we are very clever, and Todd already knows this. When we draw a NAND gate as a single circuit, we draw our funky D thing again with a little circle on the end of it. And there's my not AND gate.
It's like a really fat man.
Oh, I'm going to draw the whole thing again. That was pathetic.
It's a pathetic funky.
All right, so there's my NAND gate. My NAND gate is a not AND. If you were to draw it as 2 elements in a circuit, it's an AND gate with a NOT gate before the output. It's really simple. When you draw your truth table, Draw your truth table for an and invert it. All right, so here's a not or gate. Now, can you stop, please? So when I draw a not or, again, draw my or gate and put a circle in front of it, and out we go. So once again, a not or gate inverts the logic of an or gate. So and when you're saying the logic out loud, one not or one nor one, what's the output? 0. 1 nor 0? 0 nor 1? 0 nor 0. Very good. We've just done a straight invert of a NOR gate, of an OR gate. This is a NOR gate, not OR. Very simple. Last one. This one's interesting. There are other logic gates to draw from here, but this is the one where this is where we stop. We just do these 6. And the question that should be asked sometime soon is, do we have to know these? Yes. You will not be given what the symbols mean. But this one is exclusive OR. So, once again, I'll draw the diagram again, because this is where this one looks different to everything else. So if I draw the circuit again, and there's my light. All right, we know that if we turn on either of those gates, the light will come on. However, this is a special circuit which has got magic in it, because I can't draw it any other way. When you put the second switch on, the light turns off. So your logic for an exclusive OR, exclusivity means one only. So when both switches are on, no output. When both switches are off, no output. When a single switch is on, you get an output. Exclusive OR. All right, so it can be one or the other, but not both.
How do you differentiate between this and the
What does an exclusive OR gate look like? Good question. So when we have our inputs, we have our OR gate as per usual, and an exclusive OR gets a second input there, a second curve there. Right, so that's an exclusive OR, XOR gate. Now, you should think to yourself, hey, we could do a 7th one straight away, because I've got my XOR gate, and I've got my logic here.
Isn't it X NOR?
We could do an XNOR gate, exclusive not OR gate, which would be a straight inversion of that. So exclusive NOR. I got my zeros and ones back to front, haven't I? 1, 0, 1, 0. It doesn't actually matter when you're drawing the truth tables, as long as you draw them separately. So I'd be doing the exact opposite of that. So it's 1, 0, 0, 1 for an exclusive NOR. And if you were to draw it, not that you need to, all right, but that's not, we don't have to worry about that, because this isn't done in computing. We only need to use 6 gates. All right, so there's our 6 gates. Okay, so we have 6 diagrams, 6 symbols, 6 truth tables. You need to know all of them. Now, if I've done it properly, which I have.
Is an exclusive OR made up of again a NAND and OR?
You can make exclusives. I think the reason why we learn these 6 is so that when you go through, you can create each of those as a circuit, as an individual unit of a circuit. Okay, so quick summary. AND gates. Again, we'll do our logic here. Both on to get an output. Either of them off, no output. Okay? Invert your inputs, still no output. Simple as that. Nothing on, I need a new colour. No input, no output. All right? So this is keeping the colour separate. Now that I can't answer you, Margin, because I actually don't know.
Sorry, what was the question?
how do capacitors, or transistors is actually a better word to use because it's the right one. How do transistors become these? I actually don't know.
Oh,
Can I do some research and come back to you?
I mean,
Thank you.
I vaguely know that one. Basically, transistors are the switches which can be turned on and off with an extra electrical input. So, transistor can only allow power to flow through it if it's getting power through its input. So when you have those little things,
Keep going.
when you have those little things that you've drawn out, those little circuits that you drew out before, you just imagine each of the switches as a transistor, and so you just have your inputs going to those transistors, and then another like current or something flowing around the actual main circuit, and so then however you drew that out would work like that.
Okay, so I vaguely understand what Todd said. I will need to do some more research. I'll either find a video for it or I'll make a video for it.
A really good video I had which went all the way through from transistors to full adders, but I can't remember where it was.
If you can find it, I'd like to post it so we can actually have it. All right, so once again, OR gate, any input gives an output, etc. A not truth table, we don't need the bottom half, is an inverter. Simple as that. Not OR, a NOR truth table, inverts an OR table. So 0, 0, 0, 1. That one's drawn properly. So, yes. I think so. Okay, and once again we have a NAND table. Oh, that one's wrong. This table is wrong. This table is inverted. So, see how I got my NAND gate is around the wrong way. Because I'm supposed to have two inputs and one output. Right, so a not AND inverts an AND table. An exclusive OR gives you one of each. Right? That's all there is to it. I'm going to keep it as simple as that. I'm going to stop the recording somehow.
Magic.